The things I want to look at today are continuing with characteristics of functions, and we're going to start looking at what happens if we take one of those basic ones and start modifying it in some ways. First thing I'm going to look at is something called stretching, which you all know what the idea of stretching is. Stretching or shrinking. With respect to functions, it means a very specific thing. What it means is, let's suppose we have the basic function, the absolute value, because it's a nice one to show it on. It shows up very well. If you remember, the shape of the absolute value is a V. If we multiply that function, the function is the absolute value. If we multiply that by a 2, what's going to happen if we make our XY table? Here's our, they're out of order. Here's our original function, just the absolute value. If we do twice that, we'll get those numbers. And if we plot both of them, there's our original function, the straight absolute value. When we multiply it by 2, what we're going to get is still going to be that V shape. But what we've done is now it's as if we took that red line, anchored the vertex where it is, and pulled on the rest of it, to pull it away from the x-axis. That's the idea of what they mean by stretching. Stretching always applies to pulling away from the x-axis. We didn't change where it's anchored, but we've pulled all this upward. That's referred to as stretching. And that happens if you take a function and multiply it by a number greater than 1. Stretching is multiplying by a number greater than 1 outside the function. If we multiply by a number between 0 and 1, I'm only multiplying by positive numbers. We'll deal with negative shortly. If I multiply by a fraction, that's what the XY table would look like. When we graph it, what we're going to get is it pushes it down toward the x-axis. Still anchored in the same place. We're not pushing it across the axis, but now we're squeezing it down toward the x-axis or shrinking it, making it smaller. That happens if you multiply outside the function by a fraction. Stretching is a number greater than 1. Shrinking is a number between 0 and 1. And that all of those multiplications occur outside the function. So instead of an absolute value here, we could have had an x, the straight line. Remember what the multiplier for x is? It's a slope, isn't it? What happens if you take a straight line and keep increasing the slope? It does this, doesn't it? That's going to do the same thing with that's the same idea as stretching it. You're pulling it away from the axis. Now in this case, this is all on one side, so it makes it very clear. If we were doing a straight line, I want that in red. If we were doing a straight line, the line would be like this. If we multiplied it by 2, it would be like that. So it's pulling on both sides. You're pulling this way. This was the original, the basic one, and as we stretch it, we're pulling here. We're not changing the anchor. That should both those lines should be going through the origin, so bear with my drawing. But it's pulling it on both sides away from the axis. So that's why it didn't work. What happens if you have an absolute value and you have a multiplier inside? Well, for absolute value, you can actually take that number out. There's a property for absolute value that says says that the absolute value of a product is the product of the absolute values. In other words, the absolute value of A times B equals the absolute value of A times the absolute value of B. So this is a product. So we can split that into the absolute value of 2 times the absolute value of X, but the absolute value of 2 is just 2. Doesn't change anything to remove the absolute value. So now what we have is the absolute value of 2x is just a stretching, because that's exactly the same thing we looked at on the previous slide. So stretching or shrinking, and they refer to it as vertical stretching or shrinking, but that's really the only kind we're going to talk about is vertically. If A is greater than 1, it pulls it away from the x-axis. It does not move the anchor point. The anchor point stays where it is. All we're doing is then pulling the rest of the line away from the x-axis on both sides. That's when the multiplier is outside the function. Notice now we've gone to a more general form, just f of x. We're not any specific function. But you multiply outside the function, and I'm very deliberately stating it that way as being outside the function, because in a minute we're going to look at inside the function. So outside the function, if it's greater than 1, it stretches it away. If it's between 0 and 1, or in other words, if it's a fraction, it squeezes it down toward on both sides. Just like that straight line, if it's a slope of 1, we multiply it by a half. That's a slope of a half, which is like rotating it about the origin and moving it closer to the axis. That's shrinking. So stretching or shrinking is a multiplier outside the function. They have horizontal. You can look at that. I think it just confuses the issue more than it helps, so I'm going to skip this part. But there is a similar type of description talking about horizontal stretching and shrinking, rather than muddy the waters any more than they are. I'm going to skip that part. And the only kind of stretching that I will be working with you on is the vertical. Okay, reflection. So stretching is one way we can take a basic shape and modify it. Another way we can modify it is to reflect it. You all know what a reflection is in a mirror. Well, what we're going to talk about here is reflecting across a line, which is really the idea of, if I have a mirror here, I'm looking at it, it's being reflected at this plane where the mirror exists. So the image in the mirror is exactly as far away from this plane as you are from the plane on this side. On the straight line, because we're in 2 dimensions, not 3, that's what's going to happen with the reflection. It's going to be exactly as far away from that line when you reflect it as it was before. It's just going to be on the opposite side of the line. So a mirror image across the line, reflecting across the line. We're only going to talk about it with respect to reflection across axes. Let's look at an example to illustrate it. Well, I'll go ahead and say it. If you want to reflect across the y-axis, you multiply outside the function by a negative number. So this is really a -1, right, times the square root of x. Remember what the square root of x looked like? It looked like the red line. That was our square root of x that we looked at yesterday. Here is the xy table for that. If we just change this to a negative, it looks like this. And if we plot the blue line just flips over. It still has the same anchor point on the axis. All we've done is flip it over. If you had the straight line that we looked at a minute ago, if you multiply that by a -1 outside the function, it's just going to flip it down like that. Just flips it over about the axis. These 2 points are exactly the same distance away from the x-axis. These 2 are the same distance away, etc. Just like this. These 2 are the same distance from here. These are the same distance. So it's a pure reflection. You get it by multiplying by a -1. Yes. It's a flip about the x-axis. So I guess you could say that's vertical. Yeah. It's flipping it up and down. Up and down is maybe an easier way to say it. So if it's originally down here and you multiply by a minus, it's going to flip it up here. If it's up here and you flip it, it's going to do it down here. If it's both sides, it flips both ways. You know, what's above goes below, and what was below goes above. How about if we put the minus inside the function? My function is square root. We just looked at the minus sign outside. That flips it up and down. What if we put the minus sign inside the function? So now it's the square root of minus x. Well, here we have to be a little careful because remember we can't take the square root of negative numbers and plot them. So we're going to have some restrictions. Here, if we make our table, square root of x has this xy table. It's undefined in the negative numbers. If x is negative, it's undefined. 0 is fine. But if I put a negative on x, then that changes. Now, if I put in -4, I'm going to do minus a -4, which is +4, and I can take the square root. If I put in -1, minus a -1 is 1, and the square root of 1 is 1, 0. But now if I put in a positive number, then I'm taking the square root of a negative number, and I can't do that. That's undefined. But it does exist, and you just have to be careful when you're when you're calculating the outputs, that you don't calculate something that's undefined. But if you pay attention to that and then plot both things, you will get this result. The red line is the square root of x, the thing we looked at a minute ago. The blue line is the effect of putting a negative sign underneath the radical, putting a negative sign inside the function. What happened was, it's like taking this and flipping it horizontally. Flip it across the y-axis. So a negative outside flips it up and down, a negative inside flips it left and right. It is completely symmetric about the y-axis. So summarizing, if you put the negative sign outside the function, you reflect it across the x-axis, flip it up and down. If the negative is inside the function, flip it left and right. And so in this general form, it indicates that that works for all the different functions. So it's not just for specific ones, it's for all the functions. Another concept is symmetry. Symmetry is defined that if, and we're going to define it with respect to both an axis and the origin. Symmetry with respect to an axis is defined such that symmetry with the y-axis is that if we take x and replace it with -x, we get the same values for y. That's symmetry with respect to the y-axis. So I can x values over on the right side of the y-axis, if I put the same magnitude but negative x, and if I get the same y values, it's symmetric with respect to the y-axis. Symmetric with respect to x-axis is if I take y and replace it with -y, and I get the same x values. Example, here is a function, y equals x squared plus 4. You know what that is? That's a parabola. You know what it looks like, and obviously it's symmetric, and because of where it is, it's symmetric with respect to the y-axis, isn't it? But let's show it mathematically. The test, if you don't have the shape, maybe you don't have that graph, and you don't have to draw a graph to see the symmetry. What you can do is take the equation, replace the x's with minus x's. Wherever you have an x, put a minus x. So I'm going to put a minus x there in place of the x. But what's minus x squared? It's x squared, which is exactly what I started with. So this value of y is going to be exactly the same as this value of y. So y at minus x is the same as y at plus x. That's symmetry with respect to the y-axis. If you start with an equation, replace the x's, and if you can get it to where it looks exactly the same as where you started, it's symmetric with respect to the y-axis. That's an example. Those are equivalent, therefore it's symmetric. Okay, here's another one. Only we're defining x now in terms of y, which up to this point we've always used x as our independent variable. There's no requirement that you use x as your independent. You could use y. It works just as well. It's just that you have to rotate all of your rules. It's no longer your vertical line test. You'd have to switch it to looking this way to be a function, that sort of thing. It just rotates things, but it works exactly the same way. If we want to look at symmetry with respect to the x-axis, what we're going to do is take the y's and replace them with minus y's. And if we wind up getting exactly the same thing we started with, it's symmetric with respect to the x-axis. So if you replace x and it's the same, then it's symmetry with y, so with respect to y-axis. If you replace y and you get the same thing, it's symmetric with respect to the x-axis. And that's what it looks like for that. That's what we've just been working with. And you can see from the graph that it's symmetric. Equation like this, we can check both x and y. If I replace x by minus x, I'm going to get this same thing back again. I'm going to replace, if I replace y with minus y, I'm going to get the same equation back again. And so it's symmetric with respect to both axes. And if you realize what this graph looks like, then it would be obvious. That's a circle centered on the origin. So it's symmetric with respect to everything. What about this example? If you replace x with minus x, you're going to get this, minus 2x plus y equals 4. That's not the same thing, is it? So it's not symmetric with respect to y. We'll replace y with minus y. You're going to get this. That's not the same thing as that. So it's not symmetric with respect to the y-axis either. Or, I'm sorry, the x-axis. It's not symmetric with respect to either. And from drawing graphs, you know that's going to be the case for most functions. They're not going to be symmetric with respect to anything. And that's the way you would show it mathematically, is by replacing the x's or the y's. Symmetry with respect to the origin. That's a third type of symmetry, and it's kind of a strange one. Mathematically, it's very clear, but graphically, you have to kind of combine a couple of things. Symmetry with respect to the origin. means that if I replace both x and y with their negatives, I have to replace both at the same time. If I do that and I wind up with the same equation, then it is symmetric with respect to the origin. Here, if I replace x with minus x and y with minus y, I'm going to wind up with exactly the same thing, won't I? Therefore, that's symmetric with respect to the origin. But think about it, that's a circle on the origin. I mean, it's centered on the origin, the same distance all the way around, so it's symmetric no matter which direction you take. So that's pretty clear for that one. Well, let's take a different one. Let's take that one. Remember the shape of that one? The cube. The cube looks something like this. That sort of an S shape go through the origin. Let's test symmetry with respect to the origin. Replace both x and y with their negatives. If you cube a negative, you get a negative, right? Because you have three negatives. But then I can multiply by minus 1, and I'm back to where I started from. This equation is symmetric with respect to the origin. And let me bring back my... what you kind of have to do is you have to kind of think of flipping it twice. If you flipped it over here and then down here, if you can work with that concept, then that's kind of the way it works. It's not symmetric with respect to the y-axis. It's not the same over here as it is over here. It's not symmetric with respect to the x-axis, but it is symmetric with respect to the origin because you can do the double flip and it comes out to be the same thing. So 3 types of symmetry. So the concepts from this are, you can have symmetry with respect to the y-axis, which is left and right. You get that by replacing x by minus x, you get the same thing out. It's the same thing as putting a negative inside the function. You can get symmetry with respect to the y-axis. That's where you replace y with minus y if you get the same thing. It's symmetric with respect to the x-axis. And you can get symmetry with respect to the origin if you replace both and wind up with the same thing. Now, one of the properties of this, 3 different types of symmetry, is that if you have both x and y symmetry, you will have symmetry with respect to the origin. If you have both of those. In fact, if you have any of the two, you'll have the third one must be true. You could have symmetry with respect to the origin and not have either of the others. We saw that on the cube. That it was symmetric with respect to the origin, but not symmetric with respect to either axis. But you can have symmetry with x and symmetry with the origin. It must be symmetric with y then. Or any combination of 2 forces the third one. But one doesn't force the other 2. So this is what they look like. Symmetry with respect to the x-axis, same thing above and below the x-axis. With the y, same thing left and right. Symmetry with the origin is the double flip. Also related to these function basic shapes, something called even and odd. You know what even and odd are, referred to integers. In functions, an even function is a is a function defined such that if you put minus x in, you're going to get the same thing as if you'd put x in. That's the same thing as being symmetric with respect to the y-axis. So an even function is symmetric with respect to the y-axis. An odd function is if you evaluate that function at a negative number, you will get the negative of what you would get with x. That's symmetric with respect to the origin, like the cube. And it turns out for polynomial functions, odd and even exactly coincide with the odd and even integers. If the exponent is an odd number, it's an odd function. And think about it. X to the first is a straight line. Where was I going with it? Oh, it's a straight line. X cubed is that. Both of those are symmetric with respect to the origin, but they're not symmetric with respect to either axis. X squared looks like that is symmetric with respect to the y-axis. All the even numbered exponents are symmetric with respect to the y-axis. So odd functions have odd exponents, even functions have even exponents. That's kind of a basic, that applies for basic functions. When you start getting combinations of more terms, you have to actually check it. Sometimes you can look at it and tell. The test is to put the negative in and see what happens. Put negative x in for x. So you want to evaluate this at minus x. So evaluate this function at minus x. And once I go through all the simplification, it turns out for this function, it gets me right back where I started from. Or in other words, f of minus x equals f of x. This is an even function because f of minus x equals f of x. Even function. And notice the exponents, even numbers. Here, put minus x in, so evaluate that at minus x. And you wind up getting minus 6x cubed plus 9x when you simplify, which is minus this. So f of minus x equals minus f of x. That's an odd function. Exponents are odd. That's going to be consistent with polynomial functions. If all of the exponents are even, it's an even function. If all of the exponents are odd, it's an odd function. If you have a mixture, it's neither. So you put minus x in here, and you wind up with that. This is not the same thing as that. So that's neither odd nor even, because it has a mixture of exponents. Some are odd, some are even. So you could have odd, even, or neither types of functions. That's helpful when we start looking at trying to analyze the behavior of an equation without having to do a huge amount of plotting and looking at it in a lot of different places. Having some tools of this type can help you get some general idea of how the equation behaves. So if you're predicting something from data, like we looked at yesterday, take a set of data, match an equation to it, predict what's going to happen. This can help you have some understanding of what that's going to do. while I'm on that, I mentioned yesterday we looked only at plotting straight lines, at fitting straight lines to data. But I mentioned that the graphing calculators have many more built in. Polynomials, exponentials, all kinds of things. And so you can get different, you can select different ways to fit equations to data. When you do that, understanding what's going to happen with the function because of its general characteristics, such as what we're looking at right now, is helpful in understanding or in deciding which of those equations to pick. If you know that something is going to continue to increase, then you don't want to pick something like a parabola, which is going to go up and then come back down, because you wouldn't be able to use it but for a very short period of time, and then it's no longer valid. So you would want to pick something that eventually keeps going up. Okay, so we've looked at some basic shapes. We've looked at doing a couple of things with them. We've stretched them or shrunk them. We've reflected them. And we've looked at some things like symmetry and odd and even. Let's add another one. Let's add a translation. Let's go back to that basic V shape of the absolute value. Now what we're going to do is we're going to take this basic shape and we're going to subtract a number from it outside the function. That's outside the absolute value, so subtract it outside. If we do our XY table, here's our absolute value. Here is that minus 4. Basic shape here. If we plot the blue one, it's going to be down here. The effect of subtracting 4 outside the function was to take this basic shape and just move it down. The anchor point moves down 4 units. You move it as far down as that number is. If this were a plus sign, we would have moved it up. So a number added or subtracted outside moves it up or down in the direction of the sign. Plus up, minus down. Does not change the shape of the function in any way. We can change the shape by multiplying it. We can change the direction it opens by using a negative. But adding or subtracting a number outside moves it up or down. No matter what your original graph is, if it's a function, plus outside moves it up 2 units, minus outside moves it down. So this is the general relationship. Doesn't change the shape, just moves it up and down. Translation. If you put the addition or subtraction inside the function, it's going to move it left and right. So here's our absolute value function, but now we're putting it inside. If you do the same calculations for your XY table, here's your original graph. If you plot the blue graph, it's now going to be over here. If you plot these points, they'll be over here. The shape did not change. It still has the same slopes to the lines. It is still the anchor point is still does not move up or down. What happened is it moved to the right. 4 units. Whatever this number is, that's how far it's going to move. But with the sign inside the function, it's going to move the opposite direction. A minus is going to move it to the right. A plus will move it to the left. So it's backwards on the sign if it's inside the function. So this is the general relationship if the addition or subtraction is inside the function. This is the summary in words. That's a horizontal translation because the subtraction is inside, or the addition is inside. And watch it. If you're moving vertically, the sign makes sense. But horizontally, remember to do the opposite. Minus means to the right, plus to the left. And this is a technique which I think is more confusing than helpful, but if it helps you do it, then use that. I just think if you can remember minus to the right, plus to the left, that's the easiest way to remember it. With the combination of things we've just looked at, stretching and shrinking, symmetry, reflections, and translations, we can now fairly simply plot some graphs that contain several different things. This is no longer a basic shape, but it's based on a basic shape. It's based on the absolute value. And I remember I said yesterday the absolute value is going to always have a V in it somewhere. This is an example where what's happened is we have translated it horizontally by that +3 inside. We have reflected it up and down, by the minus outside, and we've translated it up and down. So you could start with the basic function, translate it. You could start with it here. Translate it over to here, because it's a plus, so you go here. Reflect it so that it goes down here, and then move it up, and you finally wind up here. So we're really just kind of stacking these transformations one on top of another. If you're trying to get a quick, rough graph of a function, that can be very useful. If you're not needing high precision, but you just want a general idea, being able to look at an equation like this and say, oh, that's going to be a V shape that we've shifted around and reflected. That can be very helpful. If you know, and since there's no multiplier here, it's not going to be stretched any, so it's going to be, the slopes are still going to be plus or minus 1 on your V, and all we've done is move it around and flip it up and down. One thing with the absolute value, you have to remember that idea of the absolute value of a product is a product of the absolute values. And so if you have a common factor that can be removed, you should remove that. So we're going to take that and take that 2 out, because that's a common factor, which gives us that, which now we're down to this is the function that we want to plot. That one now we can recognize as being a V shape, which is shifted to the right by 2 units, and we've stretched it away from the x-axis. There's our basic shape. There's our function here. We've moved it 2 units to the right, and we've stretched it up. Another example, with the fraction, we're going to shrink it, we're going to reflect it, and we're going to translate it. We're going to move it. So we start with a parabola. We squeeze it down toward the x-axis. We flip it over, and then we move it up. So you start with a U with the vertex here. We squeeze that down. We still have the vertex here, but we squeeze it down. Then we flip it over. The vertex is here, and we've got a squeezed version. Then we shift the whole thing upward. So you can do them independently of one another. No matter what the shape is, that's a translation upward. Whatever shape it is, just move it up. That's going to be a translation to the left. Doesn't change the shape, just moves it to the left. That's a translation both up and to the right. So we're going to move it to the right, and then we're going to move it up, or move it up and then to the right. Actually, you probably ought to do the right first, and then move what results in. Work from the inside out. So, summarizing all the different things we've looked at, if you take a function and you add something outside, that's like translating it up by that many units. If you subtract, you move it down that many units. If you add inside the function, you translate it to the left. If you subtract, you translate it to the right. If you multiply by a number greater than 1 outside the function, you pull it away from the x-axis. If you multiply by a number between 0 and 1, you squeeze it down toward the x-axis. If you multiply by a minus sign outside the function, that flips it up and down across the x-axis. If you have a minus sign inside the function, flips it left and right across the y-axis.